What you see here is not just me squeezing a balloon. It's actually a demonstration of one of the chemistry laws that we'll be studying in the days to come. This one happens to be called Boyles Law, and Boyles Law relates pressure to volume of a gas. More scientifically, we could say this. We could say that in a gas, pressure is inversely proportional to volume. Now, how does that work with me squeezing a balloon? Well, as you saw, when I was squeezing the balloon, I was trying to make the volume smaller. And by doing that, the balloon resisted me because we have a trapped gas. But as I attempted to make the volume decrease, what happened was the gas particles inside my balloon started colliding with each other, and more importantly, the walls of this container, which increased the pressure. So when we say something is inversely proportional, a relationship is inversely proportional, it means that as one value goes down, the other one goes up. Now in the case of the balloon, I was trying to make the volume of the balloon decrease, and when I did, the pressure went up. So we can look at this graph here, and we can see a relationship shown by the curve that is inversely proportional. Now, we see on one axis we have pressure, and on the other axis we have volume. And we don't see any values down on these axes, but we can arbitrarily put some in. For example, for V1, I could put 5. For V2, I could put 10. For P2, again, I could put 5. And for P1, put 10. And how we could look at this and think about this is like this. As I move from left to right across the x-axis, I increase in value. But as I increase in value from left to right, we see that the red curve is decreasing on the y-axis, on the pressure axis. So at a value of 5, pressure is 10, and at a value of volume of 10, pressure is 5. So as the volume value goes up, the pressure value goes down. That is very characteristic of a inversely proportional relationship. You can also think of it like this. Here we have two pistons, and as the volume of this top piston decreases, you can see that the gas particles are definitely closer together, which means they're going to be colliding with each other and the walls of this particular cylinder. Down below, down here, you can see a cylinder with a much larger volume, much bigger space here. The gas particles are further apart from each other, which means that the pressure will go down. So here in the bottom example, we see high volume, low pressure. On the top example, we see high pressure but low volume. So as one goes up, the other one goes down. So Boyle did some experimentation, and he found that with a gas at a constant temperature, when he multiplies pressure and volume, he winds up with a constant value. Now, we can go a little bit further than that. We can put some numbers in and use this law mathematically. So what we'll do is we'll arbitrarily put in the number 1 for K in P times V equals K constant. So if P times V equals 1, we can then predict about some mathematical relationships that go with Boyle's law. For example, if P was 2, then the volume would have to be, so we'll keep the answer as 1. So what would we have to multiply times 2 to get 1? And V would wind up being 1/2, because we all know, we all know that 2 times 1/2 equals 1. So we'll go ahead and jot these in as we go here. So this would have to be 1/2. And if P was 3, then V would have to be, so what I want you to think, if P is 3 and we have to multiply by something to get 1, what do we multiply times 3 to get 1? And the answer would be 1/3. If P was 4, then V would have to be, so if P is 4, what would we multiply it by to get 1? We would multiply it by 1/4. So what I want you to see here is that as the value of P increases, the value of V decreases, because 1/2 is a little bigger than 1/3, and 1/3 is a little bigger than 1/4. Okay, so through experimentation, Boyle found that his law could be used to relate two sets of conditions, a before and an after. And how it looks is like this. P1 times V1 equals P2 times V2. Two sets of conditions. And in gas law problems, I want you to think where you see the subscript 1 as initial conditions and where you see the subscript 2 as final conditions. So in other words, what we have here is we have a before scenario and we have an after scenario. Using a little algebra, we can find the value of a variable in this equation if we know any 3 out of the 4. So here we have 1, 2, 3, 4 variables. As long as we have 3, we can always find that 4th. Okay, so what we'll do is we'll tackle an example, put Boyle's law to use mathematically. This is how many of these problems are going to look. They're going to give you kind of a little story problem explaining to you what has happened to a gas, and we have to then do the mathematics behind what we see to figure it out. So here we go. A gas is found to have an initial pressure of 2.44 atmospheres. Its volume is 1.00 liters. It's telling you very matter-of-factly that that is the initial conditions that this gas is found at. So what we would like to think here is that this is the initial pressure. So this could be our P1. And this is our initial volume. This is our V1 for that formula. What would be its pressure if the volume shrunk to a third of its initial volume? So here, 0.333 liters, we have to decide, is that a pressure or is that a volume? Hopefully we answer volume for that, so this would be then V2, which means that we don't know what P2 is, and that's what we have to figure out. So what we can do is we can go ahead and do a typical type setup for this problem and make a prediction and then follow through with our calculations. So let me clear this off the screen here. And what we're going to do is we're going to make a table of known values whenever we do these types of problems. P1, V1, P2, V2. These are all of the variables that are necessary to solve one of these types of problems. Okay? So our P1 from the previous slide was 2.44 ATM. Our V1 was 1.00 ATM. Whoops, I'm sorry, not ATM. It would be liters because it's a volume. P2 was unknown. We said that we didn't know that one. We'd have to figure it out. And then V2 was 0.333 liters. So what we can do at this point is make a prediction, and we'll see if our final answer agrees with our prediction. So what we have then is we have a gas that was initially at 1 liter. And that gas is going to get compressed at a later time to 1/3 its initial volume. So it's going to compress down to 1/3 of its original size. Now we saw with the balloon, as I compressed it down, the pressure went up. So what my prediction would be here is that my pressure is going to go up higher than 2.44 ATM because I'm decreasing its volume by 1/3. So we'll do the math and just make sure that we're correct. So again, the formula was P1 V1 equals P2 V2. Okay, so what we do then is we set it up. 2.44 ATM is my first value, and that's for P1. I like to put them in parentheses to match how I calculate this on a calculator. And it's going to be multiplied by 1.00 ATM. We have an equal sign next, and P2 we said we don't know, so I'm going to leave it as P2, just kind of a bare variable in the equation that I can then isolate and solve for. And my V2 then would be the 0.333 liters. Okay, so last year in algebra class you learned how to isolate a variable, and in this case here we're going to take our 0.333 and we need to get rid of it from the right side. We want P2 to be all by itself. So the way we do this is we divide both sides by 0.333, and what we wind up with then is we have 2.44, and I'm going to leave the units out just for a moment. So we have 1.00, actually I'll put them right back in, 1.00 ATM, and then we have 0.333 liters. Okay, actually I'll put the unit back in for the initial volume. Whoops, actually, you know what? Let's go ahead, let's erase that. There we go. Okay, so we have 2.44 times 1.00 liters divided by 0.333 liters, and that's going to give us P2. So in this case here, why I redecided to put my units back in was because I want to be able to cross-cancel units and be left with the appropriate unit. So I kind of made a decision midway through my problem. It's probably a better idea to leave those variables in there. So here are like variables. A liter divided by a liter gets cross-canceled. And what we're left with really is 2.44 times 1, which is 2.44, divided by 0.333. And if you have a calculator, it's very easy to divide 2.44 by 0.333. And when we do, we wind up getting P2 is equal to 7.33 atm, atmospheres of pressure. Does it match our prediction? Yes. We said that if we decrease the volume, we would increase the pressure. So we went from 2.44 to 7.33 atm. So quite substantially, we increased the pressure. So just for review, Boyles Law is a gas law that relates pressure to volume. It has an inversely proportional relationship. As one goes up, the other one goes down. I hope this cleared up any problems that you had with Boyles Law. Good luck. Study hard.